Hello everyone, my name is Gerd Speer and I'm your math instructor for this course, Math 300. And before we get into the details, I want to give you just a little bit of an overview. We will begin with chapter 11 and then 12 and 13, and then we'll cover chapters 5 and 6. And generally we will cover 2 sections per week. Now all chapters begin with an overview, and you're looking at the overview of chapter 11 right now. So in this case we have 5 sections, and there's always a chapter summary. So here's the chapter 11 summary. This, by the way, is one of the most important things you look at, this chapter summary, because as I mentioned in the introduction to this course, in the welcome message, your math vocabulary is all important. And so the chapter summary lists the new terms, and you're responsible for understanding them and knowing the definitions. Also, there are typically new symbols involved, and you also have those in the summary. There are more items than what you're looking at here right now for the chapter summary, but the key terms make that a high priority, because otherwise it'll be very difficult for you to understand what the words mean. You cannot think properly in mathematical terms, and the whole thing looks rather difficult and obscure simply because you didn't know your vocabulary. So this is the vocabulary section, and as I had suggested in the introduction, in the welcome message, make yourself some flashcards. In other words, a way to remember the words and their meanings. That would be absolutely important. So chapter 11 is about probability, and section 11.1 is about the basic concepts. So here's a breakdown of the objectives for section 11.1: to use basic terms in the language of probability. So here again we are back to vocabulary, and as I mentioned to you, the summary, the chapter summary, is going to be really important for you to learn the words. Then we're going to work some simple problems involving theoretical and empirical probability. So again, some words stand out. You have to know what is meant by theoretical probability and empirical probability. And then we apply the law of large numbers, or the law of averages. And then number 4, we find the probabilities related to flower colors as described by Mendel in his genetics research, which was done hundreds of years ago. And then we'll be talking about determining the odds in favor of an event and the odds against an event. So next we'll be talking about some terminology here. And so the study of probability is concerned with random phenomena such as customer demand for specific items. And of course stores would like to know what the demand is so they can stock properly, etc. Everything that's connected to the supply chain. So this is not just abstract theoretical thinking, but it has some real implications in the real world. And so what is probability? Well, that is the likelihood that an event will occur. And then any observation of a random phenomenon is an experiment. And then the possible results of the experiment are outcomes, and the set of all possible outcomes is a sample space. So these are some very basic terms that we need to know. And then any subset of the sample space is an event. So let's talk about this more specifically, otherwise it gets really abstract. So you think about tossing a coin, and we know when we toss a coin we can have heads or we could have tails. And so in this case, that is the sample space. That's all that can happen. These are all possible outcomes. Now let's say an event that we're looking for is the event of heads, of a head, okay? Then we say the probability of heads is equal to 1/2, because half the time a head will show, half the time a tail will show. We could also write as P of H equals 1/2, or we could also say P of E, the probability of the event of heads, is equal to 1/2. Okay, so that's an example of a sample space. That's the example of an event, and this is an example of a probability of an event. Then let's think about a different type of event, or different kind of probability, and that's when we toss a cup. So imagine you have a styrofoam cup or something like that, it's shaped like this maybe, and we toss it. So that the cup can land in one of three ways. It can land on its base, it can land on its top, or it can land on its side. Okay? And if you toss the cup often enough, let's say 50 times, out of 50 times you find out that 44 times it lands on its side, and maybe 5 times on the top, the big top, and 1 time on its base, the bottom. Okay. So then we can say, for example, the probability, that of course means a total of 50 tosses. So we can say the probability that the cup will land on its top would be equal to 5 times it lands on its top, divided by all possible outcomes, which was 50, and there would be 1/10. So let's formalize what we've talked about so far. And the first part would be the theoretical probability formula. If all outcomes in a sample space S are equally likely, and E is an event within that sample space, then the theoretical probability of event E is given by this formula. The probability of E is the number of favorable outcomes divided by the total number of outcomes. In other words, the number of n of E divided by the sample space. So what's important here is that the outcomes are equally likely. So when we toss a coin, we are assuming that the coin is fair. That means that heads and tails are equally likely. Now let's talk about the empirical probability formula. If E is an event that may happen when an experiment is performed, then an empirical probability of event E is given by the following formula. The probability of E is equal to the number of times event E occurred divided by the number of times the experiment was performed. So that was the example of tossing a cup. There the events are not all equally likely. As we found out, if we toss the cup 50 times, in that particular case, it landed on its side 44 times, and on the big top 5 times, and 1 time on the base, on the small bottom there. So the events were not equally likely. So that's the empirical probability formula. In other words, it's based on experiments that we observe. So let's apply what we've learned so far. Let's suppose there's someone who wants to have exactly 2 daughters. Now we're assuming that boy and girl babies are equally likely. So find the probability of success when she decides to have a total of 2 children. So when she has a total of 2 children, then the sample space would be, it could be 2 boys, it could be a boy and a girl, it could be a girl and a boy, and it could be 2 girls. So it's a total of 4 possible outcomes. The event E that we want would be 2 girls. So we can say the probability of E of having 2 girls is equal to 1 divided by a total of 4. That would be the probability of having 2 girls. Okay? That's how we do that. Now let's change it a little bit, and let's say she wants to have a total of 3 children, and she wants to have exactly 2 daughters. So what changes in this case that the sample space is different. Now the sample space looks this way. We could have boy, boy, boy. We could have boy, boy, girl. We could have boy, girl, boy. Or we could have girl, boy, boy. Or we could have girl, girl, boy. Girl, boy, girl. Or boy, girl, girl. And then girl, girl, girl. And again, the event we want is 2 girls. And when does that happen? Well, it happens in this case, girl, girl, boy, girl, boy, girl, and boy, girl, girl. So then the probability of that event, exactly 2 girls, would be 1, 2, 3 divided by 1, 2, 3, 4, 5, 6, 7, 8 divided by 8, or 3/8. So here we're dealing with theoretical probabilities because we're making the assumption that boys and girls are equally likely to be born. Here's an example of empirical probability. In a hybrid corn research project, 200 seeds were planted. So 200 seeds were planted, and 175 of them germinated. So the question is, what is the empirical probability that any one particular seed of this type will germinate? Well, it is 175 divided by 200, which is equal to 0.875. That is the probability that any one particular seed will germinate. Next, let's talk about the law of large numbers, or the law of averages. It says that as an experiment is repeated more and more times, the proportion of outcomes favorable to any particular event will tend to come closer and closer to the theoretical probability of that event. So if you think in terms of the tossing of the cup, if we had repeated that experiment maybe 1,000 or 10,000 times, then the numbers for when it lands on its side, on the bottom and on the top, would probably have changed a little bit, but not by much as we repeat the same experiment over and over again. Example 6 is an excellent way to illustrate the law of large numbers by graphing a sequence of proportions. And so here we toss a fair coin 35 times, and here are the sequences of the outcomes: tail, tail, heads, 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 etc. And now we're supposed to calculate the ratio of heads to total tosses after the first toss, after the second toss, and so on. So after the first toss, we have 0 heads over 1, that's equal to 0. The second toss, it's the same thing. 0 divided by 2 is 0 also. After the third one, we have 1 head, that's out of 3. So it gets up to this point. And so as we compute these ratios, we see an interesting pattern emerging. And if we plot all 35, we see it hones in on the theoretical probability of 0.5. But after the first few tosses, it definitely is far away from it. But as that number increases, it gets closer to the theoretical probability of 1/2. If we continue that, let's say 1,000 times, it'll be very much clustered around the line 0.5. Probability is also used in genetics, and a long time ago, about 150 years ago, an Austrian monk by the name of Gregor Mendel found out that the flower color in certain pea plants observed this scheme, that a pure red crossed with a pure white produces red. So he theorized that red is dominant, and he symbolized that with a capital letter R, while white is recessive, and symbolize that with a lowercase letter r. And so here, the table number 2 summarizes when the first and second parents were crossed, which one are the dominant ones and which are the recessive ones. And then when you go to the next generation, first parent, second parent, then you find out even more, the second and third generation. So when you study this table, you can come up with all kinds of conclusions. And example number 2, let's just go over that real quick here, talks about that. Determine the probability that a third generation offspring will exhibit each flower color, either red or white. Base the probabilities on the sample space of equally likely outcomes. So the sample space, of course, is, red, 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 white, white, red, and white, white. And so here is the listing of the sample space. Now for red, we're looking for dominant R. And so there are 1, 2, 3 of them. So 3 divided by 4, the probability of a red one would be then 3/4. And for white, well, there's only 1 here. So then the probability of a white one would be 1 divided by 4. So that is that probability. The next concept we'll discuss is that of the odds. And it begins with the observation that if all outcomes in a sample space are equally likely, and if A of them are favorable to the event E, and the remaining B outcomes are unfavorable to E, then the odds in favor of E are A to B, and the odds against E are B to A. So it's a very simple formula, in other words. So let's an example about finding the odds of winning a raffle. So let's say Bob purchases 12 tickets for an office raffle, and the winner gets an iPad, and there's a total of 104 tickets available. And the question is, what are the odds against Bob's winning the iPad? So it's the odds against. Well, he bought 12 tickets, and so in other words, 104 minus 12 would be 92, chances to lose. So 92 chances to lose. So in other words, the odds against it would be 92 to 12. Or reducing it to lowest terms, it would be 23 to 3. Or 23 to 3. The greatest common factor being 4 in this case, for 92 and 12. So those are the odds against winning the iPad. The last concept in section 1.1 is converting between probability and odds. And so here, let's say E is an event, and if the probability of E is A divided by B, then the odds in favor of E are A to B minus A. So in other words, if the odds in favor of E are A to B, then the probability of E is A divided by A plus B. So how do we apply that? Well, let's say in a certain sweepstakes, your odds of winning are 1 to 99,999. That's the odds of winning, okay? Or your odds of winning. So what is the probability that you will win? So what is the probability that you will win? Well, we use the formula P to win is equal to 1 divided by 1 plus 99,999, or 1 to 100,000, or 0.00001. This concludes section 1.1, and so again, let me direct your attention to the vocabulary part, the chapter summary, and so get going on your homework so you stay current and don't fall behind. All the best to you.